from Stanford, talking about dimensional duality.
So I also want to start by thanking the organizers for a great conference. I've learned a lot about a variety of subjects, and thanks for the opportunity to speak this morning. So I'm going to talk about roughly a set of 4 papers that have developed over the last year or so, including collaborations with Ofer Aharoni, John McGreevy, David Starr, Dan Green, Albion Lawrence, and Dave Morrison. So let me start by reminding you of something you know very well, that in string theory, as a UV completion of gravity, ordinary geometry and general relativity emerge in a very special large radius limit from something more fundamental, such as worldsheet conformal field theory at weak string coupling, a space-time CFT, and particular backgrounds like ADS CFT, and something we don't know more generically or cosmologically. By the same token that space-time is emergent, its dimensionality, d, is also an emergent quantity, and that'll be the main theme of the talk. So let me remind you how this works just in the regime of perturbative string theory, in regimes where the string coupling is sufficiently weak that perturbative strings describe the fundamental degrees of freedom of the theory. In this regime, as these folks explained and used, the notion of dimension is generalized to the so-called effective central charge, or effective dimension, which is related to the growth of the Hagedorn spectrum of states in string theory. So it's a famous fact that a string builds up an exponential density of states as a function of mass at large mass m, or energy more generally, whose coefficient in the exponent is controlled by the effective number of dimensions that the string probes. So if you are in a geometrical regime, it's very intuitive that the more dimensions the string's random walk has to explore, the larger is its Hagedorn density of states. But you can define the latter quantity more generally. And you do that by taking the perturbative string one-loop vacuum amplitude, expressed here in the usual Schwinger parameterization. Look at it in the UV limit, so take the Schwinger parameter tau2 towards 0, and the integrand in that limit boils down to this exponential of pi times the effective central charge over 6 tau2. Technical or semantic subtlety is that in the superstring, this is usually defined including the cancellation between bosons and fermions, so the official critical central charge in the superstring is 0. But this notion of dimension can be extracted from the individual terms in that canceling sum. So what is critical string theory, or supercritical or subcritical string theory? Well, it's just a question of whether the effective central charge of a given background is bigger, equal, or smaller to the critical value. String theory is consistent with all these cases, and the most generic case is the supercritical case. In a perturbative string regime, worldsheet consistency includes modular variance, which relates this ultraviolet density of states controlled by C effective, corresponding, as I said, to the tau2 to 0 limit of the string partition function. By modular variance, that's related to the deep IR physics of the partition function, so the lightest states that propagate in the one-loop diagram. So if you keep track of the coefficients, you find that modular invariance says that the minimal energy, which I'll denote as the minimal mass squared in a given background, is minus the effective central charge over 6 times alpha prime. Well, immediately you'll see from this that if the effective central charge is positive, including the bosons and fermions together, then there's a mode of negative mass squared that dominates in the infrared. And you might think this is a catastrophic instability for such backgrounds, but you have to be careful. These are what Aharoni and I call pseudo-tachyons, as opposed to true destabilizing tachyons, because in a time-dependent background where there's some ambient Hubble expansion, a condensing tachyonic mode may or may not cause a large back reaction on the overall background space-time. And one can have a situation where the energy density in the condensing lightest mode is parametrically smaller than that which generates the Hubble expansion. So we'll work in that regime in this entire talk, which is essentially stable. A familiar case of this is the density perturbations in inflation, which have this character. So in this talk, my goal will be to explain to you a rather simple new string duality between what you might have thought were critical strings, say 10-dimensional superstrings, on a space-time that includes a compact negatively curved component. we'll find a mechanism by which new dimensions emerge from the rich topology of one cycles that arise in this context. The first step will be to show that we can work at large radius in a solution, a controlled solution describing an expanding negatively curved space, and compute the effective central charge, determine its leading behavior precisely, and we'll see that it is supercritical. We'll show that this arises from the exponential growth of the fundamental group, a feature that I'll explain shortly, which leads to an exponential density of winding states. And we'll show that this is in precise agreement with string modular invariance. Next, this will show that these spaces are effectively supercritical. And then the effect that I'm talking about, this enhancement to the effective central charge, will become more and more strong as the space shrinks. And this will raise the question of whether at small radius, there's a better set of variables to describe these systems in which the extra dimensions take a more familiar form. And we'll find that, again, winding strings provide useful guidance in showing how it works, and we'll find that the minimal completion of the system indeed contains an integer number of higher dimensions determined by the first Betti number of the space. Finally, we'll get to so at very, very early times, one needs a non-perturbative definition of these spaces, and we'll find that ADS-CFT seems to help, and also finds a B1 dimensional torus in the appropriate to describe the small radius space. Okay, so that's the plan. Let me dwell a little bit perhaps on the motivations for this study. I think it's kind of common sense, just to belabor the obvious. Curved spaces are generic. We're used to studying, I think, probably the first two columns in the table I've drawn here, that is positively curved Freund-Rubin type spaces that are interesting in ADS-CFT, flat spaces that are interesting for low energy supersymmetric model building. But then there is everything else, and both the n equals 1 and n equals 0 cases are phenomenologically viable. The topologies that correspond to more generic curved spaces, in particular negatively curved spaces, are quite a bit more numerous than those in these other two columns, and so I think it's just common sense to take a look at these in string theory. So we can control these spaces for the usual reasons that we can control general relativity plus small alpha prime corrections at large radius. In fact, for a lot of this talk, we'll discuss a zero curvature vacuum solution. So these spaces are generic, they're phenomenologically viable, and it turns out they're quite interesting too. In the usual way that string theory corrects geometry and topology, we'll find that it produces a simple, calculable, quote-unquote quantum or stringy correction to the dimensionality of the space. So this, I think, is a generalization of the wonderful quantum geometry results that we've understood in the case of Calabi-Yau, for example. For me, this study also started from model building, as the study of Calabi-Yau did in string theory, where, for example, the positive potential energy corresponding to negative curvature or even explicit extra dimensions provides a useful contribution to the moduli potential in de Sitter model building. This got me thinking about the following question. These two contributions appear in a similar way in the potential energy, the moduli potential in string theory, and also in the corresponding world sheet beta function equations. So it got me wondering whether there's some sense in which negative curvature corresponds to supercritical dimensions. And we finally realized that the right quantity to think about is the effective central charge, and we'll see now that there is a simple lesson that follows from that. Let's be specific about what we mean by negative curvature. I already said what I mean by dimension, this effective central charge. And by negative curvature, let's take the case of completely negative curvatures, taking all the sectional curvatures to be negative. Then there's a very simple and beautiful theorem of Milnor, Margulis, related to results of Selberg and others, that shows that in this context, the density for any compact negatively curved space, the density of periodic geodesics as a function of their length grows exponentially with the length, with a coefficient that you can calculate in constant curvature cases, and we'll use that, and generally which grows at least as fast as the inverse of the longest curvature radius in the problem. So in string theory, the simple-minded thing to do with this is to note that winding strings contribute to the partition function, and since winding string masses at large radius in our semi-classical controlled description grow linearly with the mass, this is saying immediately that the sum of the winding strings themselves contributes to the Hagedorn density of states. Winding strings behave like oscillator modes in essence. So this implies that there will be an enhancement to the effective central charge from winding strings, and we'll see how this works explicitly in a constant curvature example. The sort of complement to this part of this theorem I'm quoting is that in the non-negatively curved space, the density of winding modes grows at most like a power, in fact, is bounded by the power corresponding to the dimension n of the space. So let's do a detailed analysis of this, at least in the deep UV and deep IR, in the case of a constant curvature space. So this is obtained by taking the hyperbolic space in n dimensions and modding by some group that forms a compact space out of that. There are many ways you could set up backgrounds involving this, the simplest being the vacuum solution, in which this space expands linearly with FRW proper time. This metric has zero curvature. And it's interesting to compare the covering space, which is literally just a piece of Minkowski space, to the daughter space obtained by this projection, by this group gamma. We have control at sufficiently late times that t here, which is the curvature radius of the space, is much bigger than root alpha prime. That means that Hubble is as small as you want compared to the string scale. And the basic point here is actually quite simple and almost obvious. So we've already seen that the topology of the compact space involves this exponential growth of winding states, so that'll contribute, as we'll see directly, to an enhancement of the effective central charge. In the covering space, of course, we're just doing Minkowski space. There's no interesting topology, and the effective central charge is the critical value. Modular variance relates these statements to corresponding states in the infrared. The flat Minkowski space background has a minimal mass squared at 0 as usual. But if you slice it with these negative curvature slices, that comes about in two related ways. First of all, modes on the hyperboloid have a gap in the spectrum of the Laplacian, because on a hyperboloid, the volumes grow exponentially with proper distance out from any point. And that normalizability condition then goes away because once you compactify, because the volume is finite and the zero eigenvalue of the Laplacian contributes. This will produce the necessary pseudo-tachyon mode that makes a precise agreement with modular variance for this system. So maybe I shouldn't belabor the details, but this slide just exhibits what I said in the infrared. So we do quantum fields on this, not even curved, but time-dependent slicing of Minkowski space. We first look at spatial modes on the negative curvature slices. The normalizability yields a gap in the spectrum, which is easy to calculate explicitly. The time evolution, the Hubble expansion, has the effect of making modes a little more tachyonic than they otherwise would be. You can see that by expanding the effective action for such a mode in this background. And the two effects exactly compensate and cancel in the case of Minkowski space, the covering space of our system, so that you get a leading contribution in the IR to the partition function with an effective energy that's 0, effective minimal mass squared that's 0. But this normalizability condition goes away in the compact space, so you immediately learn that the pseudo-tachyonic negative mass squared is this value. We're integrating over the time embedding coordinate last, so we're evaluating this time slice by time slice, taking into account the Hubble expansion at each time, but not integrating all the way back to the small radius regime. We'll find that the check of modular invariance works in this way, time slice by time slice, which is certainly a sufficient condition. Okay, so now if you analyze the effect of this mode, you find it is one of these pseudo-tachyons, as I keep saying, where the energy density contained in it is much smaller than Hubble. Okay, so modular invariance then predicts, given this specific value of the negative minimal mass squared, a specific enhancement to the effective central charge. And you can compute that also directly and check the coefficients. This computation is done using the mathematical calculation of the precise exponential growth in the density of states as a function of the curvature radius t and the dimension n, and includes an interesting suppression factor which in the winding string channel of the partition function comes from the fact that unlike in a winding strings in a torus whose transverse motions are free, in a hyperbolic space you have to remember that winding a string around a minimal cycle, the transverse modes form a harmonic oscillator spectrum, and if you include that and the precise growth of states, you get exactly the right value of the effective central charge. So it hangs together, and we've learned that that string theory on these compact negatively curved spaces, even if you put the 10-dimensional superstring on these spaces, it's in fact supercritical for a simple and calculable reason. Okay, so that was step one, and this was all done at large radius in a controlled semi-classical regime. Now, as you go, say, back in time, if this thing is evolving in this direction, it becomes smaller and smaller. This effect, which I should emphasize, scales inversely with the curvature radius t of the space, becomes larger and larger, and the sigma model description breaks down. So it's natural to ask, is there a better dual set of variables which might control this small radius regime? Maybe there's one that is given in terms of the more familiar time-like linear dilaton solution of supercritical string theory, introduced by these folks early on. So this is somewhat reminiscent of old non-perturbative string dualities where dimensions grow. In that case, it comes from non-perturbative states. Here, the enhanced effective dimension that we've seen so far come from perturbative winding strings generated by the topology, but otherwise sort of similar. So anyway, to answer this question about the early time description, it turns out that the winding modes are again a very good guide. In this case, it's useful to focus on the conserved gauge symmetry under which the winding strings around the B1 homology cycles are charged. So in the world sheet theory, there are B1 independent operators, independent conserved currents corresponding to these B1 Sorry about that. Okay, so it's useful to look at the symmetries of the problem. And there are B1 independent operators, independent currents, which can be bosonized by some scalars x, B1 of them, which generically won't be free scalar fields, but anyway, this suggests some B1 dimensional description. Also, a D-brane on such a space has a classical moduli space of Wilson lines that is a B1 dimensional torus, and this will figure into our ADS-CFT setup. Both of these things suggest there might be some formulation in terms of a B1 dimensional torus. And indeed, there is a clean situation in which we can show that the minimal possible completion will contain such a torus if we respect the symmetry. So let me first explain the easiest regime of control that we can obtain to describe this. That involves using the time-like linear dilaton solution, which is introduced if we include a bunch of extra dimensions. So because of that positive potential energy that I wrote earlier, that leads to a simple solution of string theory in which there's a rolling dilaton. The dilaton rolls exponentially to weak coupling. The string coupling rolls exponentially to weak coupling. The dilaton is linear in time. And in that background, the first order terms in the equations of motion for all the perturbations dominate over the second order terms and lead to an essentially renormalization group type evolution. You can also argue this directly on the world sheet. But what it means for us here is that we can translate this question I raised about the small radius behavior in this simple controlled large D expansion into a question about a UV completion of the sigma model on the compact negatively curved space. So we'll do that next, and then later we'll move to the regime where this coupling actually grows large. For now, we can keep the string coupling weak for this entire range of times that I'm studying. Okay, so Of course, there are a priori many ways to UV complete a theory like those we're talking about, which are not asymptotically free. And this, in this cosmological setting, corresponds to the standard ambiguity of initial conditions. But in this case, with all the symmetries, we can show very simply that the minimal completion preserving this U1 to the B1 winding gauge symmetry is actually a B1 dimensional torus. So why do I say that? Well, a minimal completion, as you go up in energies, will reach some UV fixed point rather than continuing to flow up and accumulate degrees of freedom. So our definition of minimal is that we start in time from some compact CFT as a UV fixed point. Given that, the existence of the winding currents, which we insist on preserving, entails, for example, if you build up the gauge boson vertex operators, you have to use holomorphic and anti-holomorphic currents J, which then allow you to also build up the momentum modes symmetries, the corresponding momentum symmetries of the B1 dimensional torus. So once you know that you hit a fixed point, then and that you have these gauge boson vertex operators, you learn that you have primary 1,0 currents J, I running from 1 to B1, and corresponding anti-holomorphic currents. You can show using simple compact CFT that implies that the current J is holomorphic and vice versa, leading to independent left and right moving symmetry currents that build up a torus. In the case of a Riemann surface, a prototypical negatively curved space, it's natural to take this torus to be the Jacobian torus. So if we take a genus H Riemann surface, B1 runs from 1 to 2H, and the Jacobian torus is defined by complex H vectors which are identified by the period matrix, integrals of the holomorphic 1 forms. To go from our minimal completion to the large radius expanding space requires a closed string tachyon condensate, which can be obtained on the worldsheet from a potential energy which is minimized on the Riemann surface embedded into this torus in a way that respects the winding symmetries. So there is a very natural and standard map in mathematics that I'm sure you all know better than I do, the Abel-Jacobi map, which maps the winding modes, the winding cycles in the Riemann surface into those of the Jacobian torus. So we wrote down some explicit models that realize this minimal completion. It's fun to play with these things using the tricks that Buscher introduced for T-duality. As you know, T-duality was generalized in various ways, including to situations like mirror symmetry or ALE and S5 duality, where there aren't both momentum and winding symmetries, and you can still play the game. So I won't go through all the details, but in the paper you can find explicit models, explicit sigma models in which, when you integrate things out in different orders, you either get the description in terms of the Riemann surface or the description in terms of the Jacobian torus with a potential that minimizes you to the Riemann surface at late times. Now, there are some caveats here. I said that the minimal completion contains a B1 or 2H dimensional torus. In the case of the superstring, where we want to impose the type 2 GSO projection such that at late times the space is stable, there aren't bulk tachyons, certainly in the examples we've found so far, that entails some extra degrees of freedom on which the GSO acts, so there's more than this torus. But what we learned from this is that the space is intrinsically higher dimensional and at least contains a B1 dimensional torus. This fits nicely, it seems, into the more general classification of dimension-changing transitions that Hellerman and company have been working through in their recent series of papers. So I've shown that given a large radius, given a compact negatively curved space and the winding symmetries, it came from something higher dimensional. You could ask the so-called inverse problem and say, if I start with a torus, how likely it is that I end up on these expanding spaces? And the GSO, if you work through these quantum numbers in the models, gets you a fair way, showing that the tachyons have to be momentum modes, which help suppress particle production, although it remains to be seen how much tuning is required, and also gives you generically some Riemann surface in terms of the dimension of the space that you get. respecting the symmetries. We assume not only that you get some Riemann surface, but that you get one which respects the winding symmetry. So we just take this as a symmetry principle. Okay, so as I mentioned before, as the thing, so at the beginning we studied a semi-classically controlled thing and saw that C effective was enhanced. Then we moved to smaller radius, but still worked in the regime of perturbative string theory and saw the minimal completion was a TB1. But the coupling is still growing. The effective coupling is still growing as you go to the far past. And if you want to address the entire background, you need some sort of non-perturbative formulation. Well, one of the nice surprises we found is that this seems to fit well into ADS-CFT. We still need to analyze this. This is just a setup that I'll present to you. But ADS-CFT sees a B1 dimensional torus corresponding to the small radius compact hyperbolic space in its own way. So how that works is as follows. Consider your favorite example of ADS-CFT, say the n equals 4 theory, and put the field theory on a compact hyperbolic three-dimensional space times time, either in the expanding vacuum solution that we've been talking about earlier, or in the conformally related metric in which the space stays at constant size. Anyway, as you move toward the infrared region of the geometry, the size of the compact hyperbolic space on the gravity side, the proper size of that, shrinks in the usual way because of the warp factor. It's also important here to go out on the Coulomb branch, introduce a shell of branes, which jumps the flux away from the infrared region, leaving a flat and flux-free small radius compact hyperbolic space in that region. Now, the infrared physics of the field theory side is that of Wilson lines, and out on the Coulomb branch, the potential energy on the moduli space of Wilson lines is small. It's parametrically smaller than the KK scale of the manifold. And so, to a very, very good approximation, the Wilson lines exist in the low energy region and trace out a B1 dimensional torus. In this ADS-CFT setup, this torus appears in the infrared, where natural physics pops out in the standard Wilsonian sense, whereas in the closed string description, it was a UV completion that we talked about, and in both cases, we find a B1 dimensional torus arising naturally. An interesting little point about this ADS-CFT, which was more or less explained to us by these guys, is that these two conformal frames complement each other in a nice way. So you might be puzzled by my use of ADS-CFT for a negative curvature space, since there's a conformal coupling which leads to has the wrong sign. That is, it leads to an R phi squared instability of the scalar field in ADS-CFT. And so at late times in this metric, you might worry that you don't know what you're doing, and ADS-CFT might break down. But on this side, you see that all that is field theory on an expanding FRW space. It's got zero curvature, and it's no better or worse than essentially any cosmological model that we're used to studying in realistic physics. On the other hand, this metric goes singular in the past, but this FRW metric goes singular in the past, but the conformally rescaled one doesn't. It just goes back to the top of the hill here. So optimistically speaking, these two things solve each other's problems, and this is a new case to consider for ADS-CFT. It has the nice feature that on the face of it, it seems to formulate not only an interesting space like singularity, but one for which the relevant degrees of freedom are these higher dimensional supercritical ones that we're finding. Okay, so there's a few applications. I think this relation between infrared physics and high energy density of states is quite a bit more general. Hubble expansion in a wider class of examples can be translated into interesting statements about the UV density of states in string theory, either at the exponential level we discussed or just at the power law level, where this interesting T-duality of Cauchy, Schultz, and Trivedi between nil manifolds and H-flux on a T3, both of which have positive potential energy but don't have this exponential growth property. They both have a stronger power law growth of the density of states in a way that's completely consistent with this T-duality, as has been shown recently in interesting work of Maloney that's yet unpublished. One can go back and do more model building with these spaces. I find them interesting for string inflation models, for example. They can be meta-stabilized. Salman and I did this exercise with a product of 3 Riemann surfaces earlier. And there are some intriguing mathematical connections. Here I'm getting rather beyond my expertise, so I'll just stop here and flash the result again. Thank you.
Thank you. Thank you very much. We have a microphone problem, but I think we can. Yes, there's a question. No. All right.
In your computation of C effective, do you think that including the fermions will make an important change?
I don't think so. We estimated that in the paper. You can estimate, the level at which the system sees the supersymmetry breaking. On the infrared side, for example, there's no such thing as a fermionic pseudotachyon, and on the UV side, you can estimate it and see that this is the leading effect.
I mean, couldn't they introduce phases and cancellations in the sum?
Can they introduce phases and cancellation? I mean,
in the sum that you do plus on summation.
Right. So I'm talking about the summed partition function. The bosons plus the fermions. I'm not...
I mean world-sheet fermions.
Sure.
So you're going to include some, in each winding sector you're going to have different fermion determinants which could introduce phases, right?
That's true, but it doesn't affect the results. I mean, we estimated...
You actually did that calculation?
We estimated the contributions of those states in the paper, and we saw that it was a sub-leading effect. Again, an intuitive way you can see that is that there aren't pseudotachyonic fermions. That's the infrared version of that statement.
Do we have any other? There's another question.
In usual T-duality, one goes to small radius, and then the winding modes become light, and then the dual description you replace them by momentum modes, but then the dual torus is large. So can you see in your derivation that the torus that you have constructed out of this really grows when the surface becomes small?
So it is an interesting question whether there are reasonable evolutions in which the torus actually grows large. That would entail a kind of crunch bang, which we're not claiming here. All we so far have showed is that there's there's an ultraviolet fixed point which has a torus in it, and what the exact initial conditions are that set it rolling in such a way that then this tachyon can appear and cause the transition is subject to various ambiguities of initial conditions that we haven't really classified yet. So I think it's a great question, but the other thing I should say to this question is just that the leading thing we find here is just, again, a setup in which the the winding modes of the Riemann surface map directly into the winding modes of the torus. We're not getting the inversion of the size of the space that we have in T-duality. That's one reason why we have to name it something new. So,
sorry.
You might have constructed a similar expanding cosmology from, say, some negatively curved 4 real-dimensional manifold. But if pi1 was 0, then you wouldn't have had any light string modes.
Wait, the statement about the exponential growth is true in general dimensions.
Right, but I don't want to have the Riemann surface. I want to replace the Riemann surface with some other negatively curved 4 real-dimensional manifold. So
you can do that. If it's negatively curved and compact, then there will be an exponential density of winding states. So could you
what
say...
if pi1 is 0? What?
No, there's a theorem. I just quoted this theorem, but it's actually quite intuitive. Where was it? Whoops, I'm sorry. So there's a theorem which shows that for any dimension, a compact negatively curved space has this exponential growth of the fundamental group. It's because the covering space has this interesting property of volumes that grow exponentially with proper distance. So when you project by some group that compactifies that, you introduce an exponential density of these closed geodesics. You might be asking about the homology, not the homotopy. The homotopy is guaranteed to have this interesting property. The homology is not. So there are things called homology spheres, which have B1 equals 0, and that is actually related to this last.
Was that theorem for just constant negative sectional curvature, or
no.
any
any negative sectional curvature, because the statement about the volume of the covering space can be made for just the specification of negative sectional curvature. It doesn't have to be uniform. It's a beautiful 2-page paper. This is not some huge machinery. So
Okay.
I actually kind of plagiarized it inadvertently originally because I didn't know about it. It fits in with the physics so well. But if you want to read the full theorem, that paper is gorgeous.
Okay. I think if we have no more questions, let's thank Eva again. I'm told by the organizers that you can come back